Or you can do it either way. You can do it. I'll do it with you, but you can do it at the board. So let's do an epsilon delta. So we'll say f of x is, well, we'll take the limits as x approaches -4 of, we'll say x squared plus 1 is equal to some L that you will determine. And we will find delta. So the absolute value of f of x minus L is less than epsilon for all x such that the absolute value of x minus c is less than delta.
Sick.
Okay, so remember, you're going to start with the f of x minus L is less than epsilon. So you have to figure out what the L is, recognize what the f of x is. I'm not telling you a number for epsilon, so your delta is going to have an epsilon in it.
Minus L.
17 for L.
Wait, what? Oh, yeah.
So your f of x is x squared plus 1. We just
Oh, yeah.
stick in the -4 for
I don't know where I was.
And the x minus c that we're going to try to aim for
Here's x plus 4.
is an x plus 4.
So consider. So plus so -3. Wow, that's really true, Austin. -3 is.
Oh, yeah.
Oh, it's x to -4, not to 4. Okay, that changes things. Now this is epic. We'll go from -5 to 3.
So how do we find C again?
It gives us to it in the limit.
It's the x value of x is approaching.
Oh, so with the negatives, do we use -3 or -5? Because I can't remember.
Which makes that the biggest and absolute value.
Okay, it is the biggest absolute value.
So it's -5.
Nah. So I need to show you.
I lost something along the way. Ever read the -5 and -3?
So you want to take values that are close to -4, so you take one on each side, so -3 and then -5. Where'd you get one?
Why
It's fucking -5.
Why -3 instead of just 3?
Because it's a -4 right here.
Oh, and not with the other one.
Because you're keeping the +4.
It's an absolute value of -5 minus 4 is negative.
Okay.
It's not.
I always point my epsilons upwards.
A sign of optimism.
No, not at all. I just like to run them like that. They feel more natural than to try and curve them forward.
You want to see if Howard needs a little help there?
Yeah.
Okay, so. So you got 2 here is less than epsilon. So you consider numbers between -5 and -3.
Okay.
And you're trying to make it so it's only x plus 4 is less than epsilon, or less than delta at this point. So you would plug numbers in that would make this absolute value the greatest it could possibly be. I know this.
We don't know what epsilon is.
No. But what would make, out of these two values, what would make this the greatest possible absolute value?
-5.
Exactly. So you plug -5 into that. Oh, let's think about this, boys. Would that be an
That was
negative?
negative.
Yeah, L would be 11.
So 4x minus 12.
Mm-hmm. Minus 12 less than 0.01. Because
Oh,
you gave us
'cause-
epsilon. So then you factor the 4 out of that bad boy.
Hey, that's our answer. No, it's not. That's 100. That's 100.
110 divided by 4 is still...
I didn't.
Well, that's amazing.
It's 100, not a 10.
It's not even, it's points.
Yeah, it is.
It's not.
What are they? Hold on. 20. Oh, 1. Oh god, that doesn't look like a 4.
Is that a...
Check on Alec there. How we doing, Alec?
Okay. Yeah, yeah.
You okay with that one?
Yeah, kind of.
Okay. Do you know what that is?
33, let me look. It's the one about federal spending.
I need
for
my
national
book.
defense.
What page are we on?
93.
83.
And we got through C, and then we got uber confused on how to make D.
What page are we on? Oh,
93.
oh, 24?
Number 33.
Number 33.
Number
Homework
33.
24.
Yeah, homework 24, number 33.
Oh, yeah, I switched around. Homework 24. Number 33. Gotcha. So we are trying to, here we go, a table of values. And that gives us the amount of federal spending in billions of dollars for national defense. And you're okay on A, the average rate of spending? And you're okay on B,
Average rate of change.
average rate of change, and we want the average rate of change in spending from 2002 to 2003. That's the one that was tough.
No, D in
No.
on is.
B was?
D,
D.
because it's trying to find quadratic regression equation.
Oh, okay.
And I don't know.
Okay, so that's, we're gonna have to do our regression stuff. So it's like I feel like I'm doing Mr. Hogshead's job here. So we're gonna do a little stats. So you're going to, let's see if I can show this. So grab your, you need a graphing calculator. I'm going to,
There's no way that just freezed there.
No, not that one.
okay. So we're going to go to, come on, calculate, there we go. So I'm gonna go to stat, and then go right arrow to calculate, then hit enter, and, oops, wait, didn't do that right. Back to stats, just hit enter right away. Now I got junk in mine, so I'm gonna go up arrow, clear, enter, then left arrow, up arrow, clear, enter, so I start with a clean slate. So can somebody, so we're gonna go 1900, 1990 is gonna be our first one. Should we just call that times 0? So that's gonna be your 0 and hit enter. And then we have 1995, so we'll call that 5. And 1999 is gonna be 9. 2000 is gonna be 10. 2001 is going to be 11, 2002 is going to be 12, 2003 is 13. And we'll right arrow to the second column, L2, and we're going to put in those numbers. So is that 299.3, 272.1, and 274.9, and 294.5, and 305.5, 305.5, and 348.
Mr. Street.
Did I miss one?
Yeah, you did 3.5.5.
Oh, goodness gracious. I did,
That should be 305.
that's why I didn't like that. Let me try that over again. So after 294, 305, 305.5. That looks better. 348, 36, 404.9. Okay,
You have 2 decimals in there. You
did that again.
You
Oh.
forgot to press enter, yeah.
4.9. How come I don't have the same number of numbers?
Found it. Never mind. Yeah, I found it.
It's today's 6th. I think you're right.
Yeah, you're right. Also, I found out what to do, so.
So you're good to go?
It's today's 6th.
But we also have, yes, we have one more question. It's pretty basic.
Okay, so I don't need to do any more of this?
No, it has nothing to do with that anymore.
Okay, well then, I'm out. Okay.
Our next one was, when it comes to the squeeze theorem,
Yes.
what do we put on the left and the right?
Well, that's a good question. You know, in general, what you need on a squeeze theorem is you need something on the left that's a little bit smaller than your function, something on the right that's a little bigger than your function, and they have to go to the same limit. So that's where the tough part is. It's going to have to be a pretty special case where you can find something that's a little bit smaller, something a little bigger. A lot of times what can happen, and what might happen is like with a sine or something like that, or cosine. So if we were going to say, prove the limit as x goes to infinity of sine x over x is 0 using the squeeze theorem. Now this is a pretty entry-level question there, but you get the idea. So now you need to, sine goes between -1 and 1 and all points in between, but you know the biggest it ever is 1, and the smallest it ever is -1. And now if you take the limit as x goes to infinity, you know, this is going to go to 0. And this is going to go to 0. So you squeezed it to be 0.
Oh, we have one more. I lied. And it was the limit as x goes to infinity of natural log x over log of x.
Yeah.
And we found out what the value is, but we have no idea why it's that value.
So this is a pretty tricky one here. So they're both going to infinity, both very slowly. So it goes to infinity over infinity, which is indeterminate. And we don't know anything about the L'Hopital thing yet, so that's not an option. So what we want to do is a change of base. So we in calculus love natural logarithm. So we would like to convert logarithm base 10 to a natural logarithm. And so how to do that? So if you say the logarithm, the common logarithm is a logarithm base 10. So if we set it equal to y, if you remember your change of base formula, you can go right to that, but probably unless you're a math teacher and you haven't done it recently, you're not going to remember it. But you can recreate it. So we can go to the corresponding exponential. This you do have to remember. Is that okay? Then we can introduce the logarithm we want, so we can take the natural log of both sides. Okay. Now we can use our property of logarithms to bring that y out of the exponent. Remember, the y is our logarithm base 10. Then we can divide by the natural log of 10. And so what we did, what the change of base formula says, and the y was our logarithm base 10. So if you have a logarithm and you don't like the base, you just make it whatever base you want, and then you adjust it by dividing by the logarithm of the new base of the old base. That's the logarithm, the change of base formula. So then we can come back to our limit and say, oh, this is really natural log x over natural log x over natural log 10. And to divide by this is going to be to multiply by the reciprocal.
Thank you.
And you cancel those. Now, no matter what x is, that's always natural log 10, so that's our limit. Okay,
Thank you.
you bet. Anything else?
Yeah, so we couldn't have used Libby policy.
No, not yet. Not until we teach it, yeah.
Text it again.
We did.
In the current class. We're going to do, actually, it's kind of cool. We do advanced with what we talk. So we'll go way beyond what you did last year. So let's talk about 3.1, derivative of a function. So now we have all these notations that you guys have seen before, but we're really mystifying in the past. So we have the prime notation that's sometimes called, we have f prime of x, suggestive of a function. We have what's known as Leibniz notation, the dy dx, which is suggestive of where that comes from. That whole limit as delta y over delta x, as delta x goes to 0. We know that its definition is the limit as h goes to 0 of f of x plus h minus f of x all over h. We also know that the derivative at a point, so this is the derivative function that we see here with the x in it, the derivative at a particular number. So a is supposed to represent a particular number while x is the variable. So we can say the limit is h goes to 0, and then just rewrite this using a's instead of x's. So f of a plus h minus f of a all over h. Remember, there's also the other definition here, and so you have to at least be aware of it and recognize it, because it undoubtedly will appear as some kind of multiple choice question on the AP exam. Is going to be f of x minus f of a over x minus a, so that's really just the derivative evaluated at a. And of course we also have y prime. We can use df dx. We use this notation ddx of to show we're taking this an operation of taking a derivative. So you might do something like that. It shows differentiation as a operation. Okay. So let's see if we can remember, you know how to graph f prime from f of x. So I'll give you a long involved graph of f. You can try to come up with the graph of its derivative. Feel free to come to the board if you like on this, or if you'd rather have it notes, that's okay as well. So I'm going to give you f is going to be in green. So this is y equals f of x, and we're going to say it's going to look like, it's supposed to look kind of like maybe a parabola or maybe part of a sine curve. And then we're going to go to a straight line segment. And then we're going to go to something maybe looks like part of a parabola. And then we're going to go to a straight line segment, and another straight line segment. And then I'm going to get my roll here. Yes. We'll go, looks like maybe a potential cusp coming into play there. Horizontal. Like almost a cubic. And up to isotope. And down.
I ran out of room.
Maybe a vertical tangent in there.
Remains strong.
Unknown.
Literally
Asymptote to the right.
Goodness gracious.
Oh, a little bit of everything in there.
Plus starts off. Positive. Let's make
So it's increasing from here to here.
so
So when it's increasing, it's positive. When it's decreasing, it's negative. So
Well, we're not doing it from double convex. Wait, no, you're right. Sorry, I was thinking of this already. Sorry, that you were talking about. You're right.
that's when
so
constant.
it's gonna go down to 0 because it's about to start going down. It's about your negative slope, so it's gonna go like this.
And then it goes constant for a while after, right there. So it'll be like a flat line under there.
Yeah, and here it's constant.
And then it goes back to 0 again, right? For the 1.
Yeah.
Then it begins increasing again. Not constant though.
Yeah. It's gonna be
And then it is a constant at like 2. So we go like that.
so it's increasing.
And then it goes back down
It's still decreasing.
like here. And
And then it increases right here.
then 0 to 1 there. Or as you can notice a sharp difference between this and this. Or this is curved and that's flat.
So then you have to have it as like a little loopy boy, and then it'd be a straight line. So it's the increase in here isn't constant, so
Boys, we chuck it.
Wait, so, well,
no.
Or am I losing you there?
No, he's just doing all the different. Will it not be a connected line?
No, I don't think, so anytime you have like a corner point, that's gonna be where the derivative is undefined.
So that ends up right there.
I'm thinking the first one looks kind of like a parabola, so I'm thinking it's gonna be a straight line derivative.
And
So
then
we have a
that's,
straight
so
line,
it's
it's
a
gonna be
straight line.
horizontal.
That's a positive.
It's kind of like a parabola going up, I don't know if it is or not, but it kind of looks like a parabola, so it's gonna be a straight line.
Straight line up. It's a straight line again.
So that parabola, and then it's gonna be
Oh, is that a different straight line? Yeah.
and this one's a straight line until about
Then, oh, cusp. That's a thing, isn't it?
cos? Yeah, cos.
I would hope so.
it's supposed to be a straight line. It goes to there.
So since this increases, when it
And that's the next, like the next cube,
It
so
would
it
go
become a parabola right there. So it'd be like that.
What do you Why do you have a line in here?
Similarly,
This straight line right here,
except that's gonna be negative.
that's supposed to be straight. It's supposed to be that right here.
Wait,
Yeah, so then, oh, because this is that.
Well, think about it. This is a straight line, which is just 2, which means it would have to be 0 when you take the
Oh,
derivative.
yeah.
So it's just increasing, so that would be like that.
And that's really, it's gonna be a negative. That's the trust.
it starts.
Okay, then it's decreasing there. Oh, vertical tangent like that, right? Or there's the vertical tangent, right? And it has a.
Is it a vertical tangent? Wait, okay. Never mind. Not what I did. So the vertical tangent is gonna break there.
It's an x cubed. And then we're gonna have another one. And we're gonna have another parabola. Yeah,
Negative.
negative parabola.
Is it a whole parabola?
I don't think it's a
Yeah, you got the
whole.
same parabola.
Parabola.
Oh yeah, no, because it goes to a vertical.
No, it does, it does.
No.
Is it?
Vertical tangent makes it die.
Yeah, so then there's another.
Then it just decreases to a
so that means there's another,
horizontal.
there's another
So it's a-
asymptote.
Yeah.
With that vertical tangent.
So then
And then we have,
I've got this little section left. So it's still negative.
so it's gonna be wait, that's an asymptote, no?
Yeah, it has an asymptote, so.
So it should go like, huh? Right?
Yeah, because it's
I
gonna
think
be.
so.
It starts really high negative,
Yeah, it's gonna be, yeah. And then it slowly goes until it's 0 slope.
That was brutal.
That
Way
was.
to just throw us into the middle of it.
I forgot about this.
Well, see, we usually don't do.
Yeah,
that.
we went from 0 to 150.
Imagine trying to track something that's moving like that.
Yeah, we just told him we didn't know how to swim, so he threw us in the ocean and
Yeah.
voted away.
Be ready for a little find f from f prime?
Yeah.
Yeah.
Yeah. Correct answer.
This time I'm gonna not make the mistake of making my graph huge.
You mean too small?
No, look at how big it is.
I know. But if you will just keep going, so we'll just wait till he's done. How about that?
Yeah, that's
This
fine.
is going to be f prime, Bex, so you're going to try to come up with
Well,
and we'll say f is continuous.
Okay.
that helps a lot. Let's go back on. I knew there was another U.
I was thinking continuous and then a slope of like -3. Alright, fine, I guess we're not waiting for him to actually hit 0. So it's gotta be up further, because it's gonna have a slope of -3, but it's gonna hit
Bruh.
0.
Bruh.
So that one has a slope of whatever that is. I'll go with like 1 or 2.
I'm gonna wait. Then that one's also just a straight line. Or this, those are straight lines.
And it has, this
Bam.
has to be a corner point.
Bam.
It has a slope of like -3 or something.
Is that a asymptote? Yeah.
Okay, I should be on the other side of it. Oh no.
Oh yeah, I need to make it all the way to 0 with this.
Yeah, so it's just,
And there's no y values, so whatever we get should have the basic same shape, but maybe different, maybe translated up or down.
Yeah, it would be like a little,
I think it's a cross right here.
yeah,
So positive this.
I know it's gonna swoosh up. And then it's a corner point.
Wait, no, it's still increasing, so it's gonna be
Down to
it's gonna go
0.
like that.
And it's increasing again from there to there.
And then it's still increasing, it's just not like as, it's just gonna be like a downward, you know what I'm saying? Like it's gonna be like, yeah, like that.
I am this very good.
Man, since you're calling it that. What have you done?
I ran myself right off the board. Not good planning.
And then this little,
So is that, yeah, that's
It's
gonna be
gonna
a
go more.
tangent right there, you think? What I'm trying to get at.
This is gonna come down to here.
Yeah, so that's the
And this
vertical
is gonna
tangent.
be added
I
on.
should have wrote it on the same.
no, the vertical tangent's gonna be right here.
So,
Because right now, we are right here.
yeah, I know. I'm trying to think of what we're doing here.
Vertical
Before we hit
tangent.
the- before we.
It's gonna be just a swoop up.
Just a swoop diddy loop, scoop diddy loop.
Yeah, because the slope is increasing.
Yeah, you're right. Also, that was the cleanest, like, sloop I've ever done, and I'm so sad because I have to mess it up.
And then it is still gonna be positive, but it's gonna be lower.
And then I think I wanna hit actually.
So it's still positive, but then it.
So it's copying up on both sides, so it's gonna be like a cusp then. Right? No, never mind, no. I'm thinking too hard.
Because
So when it goes to the same infinity, we have a vertical tangent.
Mm-hmm.
Different infinities is gonna be a cusp.
Oh, okay, so that's right.
So it's going to positive infinity on this side and negative infinity on the other side. And then so this is supposed to be tacked on up there.
Yeah.
Okay,
It's
I
gonna
was
go
like,
up to the cusp.
can we just do that? This can.
Oh,
So you have to move this piece of the board up here.
This is like,
So the A's are in the same place. These are the same points. But I ran out of room and I didn't want to write on the board, on the wall.
So then it's
Yes, I could.
another.
This is pain.
yes.
That looks like a really weird horse.
Or unicorn.
Ah, yes. Unicorn.
I don't like it.
I don't like it.
I don't like it.
There you go. Now it is a unicorn.
All right. Questions on that?
Why?
Okay. Why not?
Because pain.
Well, yeah, just
Okay.
Passing the first.
So then we'll go
one,
on, we'll talk about some one-sided derivatives. And look at some, let's take a few notes on this.
Oh,
Then we'll see if we can get you back up here. One-sided derivatives.
we're just looking to take notes at the board, boys.
Well, you could do that too, yeah. Take what you-
Just write what he wrote. It's like old English classes.
So we look at, the idea is if we have something like, say, the square root of 4 minus x squared. So that, if you remember, do you remember what that looks like? Yeah, it's a semicircle, top half, radius 2, so you get something like that. So the question is, does a derivative exist at these endpoints? And we can answer that question without defining it, but we kind of need, at least mathematically, you know, how do you define a derivative when the function is not defined to one side or the other? Because the limit definition, which, remember, the derivative of a function is that limit as h goes to 0 of f of x plus h minus f of x. Now, it's a true limit though, so h can come in from both sides. Well, how do we do that when it's not defined on the other side? Well, we just say the limit as x approaches 0. You know, if we're coming in this way, it would be from the right. So if that limit exists, then we say that the derivative exists at that point. And if we come in from the left, then we would just make that be a negative. And if that limit exists, then we say the derivative exists. So I won't write it all out because I think it's a lot of words to say essentially that.
So is there an answer because the derivative exists
Well, all right, well, we don't have to do the actual definition, so that's what, good point. So the real question is, so what do we do? And we want to know, does f prime of 0 exist? Does f prime of negative 2, I guess we would say. Negative 2 exist, or f prime of positive 2 exist? But we can still do this, like we would using our power or chain rule. So we know this is 4 minus x squared to the 1/2. So f prime of x, we can say, is going to be, it's been a while since we've done chain rule.
1/2 4 minus x squared to the negative 1/2
Times,
negative 2x.
remember that? Okay, and so a little cleanup, we can cancel the 1/2 with the 2 and the negative 2x. So that's going to look like the negative x, and then the square root of 4 minus x squared in the denominator. Does that look familiar? So if we say, what is f prime of 2? Well, you're going to plug in a negative 2, and we're not really doing the limit, but I think we can see what's going to happen. Yeah. And you can see it's going to be a negative 2 on top, but this is going to get really, really small. And so in our semicircle, what's happening is, as we look at the slopes of the tangent line, that's going to actually go straight vertical there, which means it's not going to exist. And the same thing on the negative 2 side. Okay. Okay, so where this comes up more is probably on piecewise functions. And then you got to be a little careful. And these are popular choices on AP exams also. So in general, a derivative exists if, and this is the part that can get you in trouble too. First of all, it's got to be continuous. So when you have a piecewise function, if you're not considering the continuity piece, you can be misled, because you can get a piece that comes in here and a piece maybe that comes in there, and I didn't do that very well, maybe there. And so as you come in, those slopes of the tangent line are going to be parallel. And so you say, oh, the left-hand derivative is equal to the right-hand derivative. But if they aren't connected, it's already not possible for the derivative to exist. So you got to get continuity first and then look at the left-hand and right-hand derivative. So in general, derivative exists if first the function is continuous. So you'll always be looking for continuity. And we can say then the left-hand derivative equals the right-hand derivative. So that's what we're looking for differentiability, for the derivative to exist. So let's look at a few of these. So these are a little more sophisticated than we might have done last year, but because we've got some experience taking derivatives that we didn't have at this time last year, hopefully this will not be overwhelming.
Didn't we just prove today that we didn't learn all that last year?
Well, I remain optimistic. So, question is, does f prime of 0 exist? So,
Because LH doesn't equal R.
so first is a continuous. So you plug in 0 into both pieces, you get the same thing. So we check the continuity box, right? So continuous, yep, it is. So then we go left-hand derivative. So left-hand derivative is going to be 2x. Evaluate that at x equals 0, we get 0. Right-hand derivative is going to be, and that's true for all values, so evaluate it at x equals 0 is still 2. And since left-hand derivative is not equal to right-hand derivative, and the answer is this doesn't exist. See how the kind of the plan of action is? So let's do g of x. We'll call this g of x is say, x squared for x less than 0 and x cubed for x greater than or equal to 0. And maybe we should look at a graph here too. So what this is also saying, I'll do this real quick. So on the left side, you've got a parabola, so we know what that looks like. And on the right side, you've got a straight line, slope 2x. And so it's continuous, they're connected, but you can see that the derivative on the left is kind of gently coming down here, you know, like you're landing a plane without a bump, and it's going to be 0. And you're taking off real sharp there. So you have the left-hand derivative and the right-hand derivative are both finite numbers, but they're different finite numbers. That makes it a corner point. Okay, how about the next one?
Yeah, it does.
So, is it continuous?
Yes.
Yep, so it checks that box because you get 0 in both cases. And the left-hand derivative is going to be 2x, so at 0, that's going to be 0. And the right-hand derivative is going to be 3x squared, but at 0, that's also 0. So the derivative, g prime of 0, does exist and is equal to 0. So it goes to how these connect, not just because in like an AP prep, you're just worried about how, do they connect or not. So here, if you imagine somehow, even though it's not clearly obvious when you try to imagine it, the x squared coming down here and the x cubed coming in this way connect in a way that is smooth. Okay, there is no corner point there. The derivative remains defined all the way through there. Okay, so even if you zoom in on that, if you zoom in on that on your calculator over and over and over again, it's never going to look broken. It's going to be, we will say, locally linear. Eventually, if you zoom in enough, it's going to look just like a straight line because it is differentiable. Okay, well, that's the next real brief differentiability. You've seen this before, right? So differentiability is 3.2. So there are 4 ways the derivative, so a function is differentiable if the derivative exists at that point. So there are 4 ways that the derivative does not exist. You remember? Corner point. Right? Cusp. That's another one. Discontinuity and another. Yes, vertical tangent is called. Okay, I didn't get to talk to, there's a new thing we haven't seen, the intermediate value theorem for derivatives. So you might take a look at the supplemental video. It's real short at the very end. And it's not a big deal, but I think you will see a problem on your homework on that. So that would be worth taking a look at. Yes. All right.
What was that? It was a pro. No, it was